limits.
So hey guys, good morning. My name is Cosmo Casalas. I'm the Career Services Coordinator here at the Tulare campus. So really, what does that mean for you? So in a nutshell, I kind of serve as the connection between student and industry partners and employers. So I oversee, career technical ed programs here in Tulare. So the entire ag division, which is about 8 or 9 programs, graphic design, welding, and architecture. But with that being said, I'm here to help all students on this campus, regardless of what their major is. So some of the things that I can help you with, my big one seems to be building resumes with students, mock interviews, and then searching for internship opportunities and work experience. Depending on what your major is, the requirements for program completion may be for you to complete work experience hours out in the field. So I can definitely assist you with that if that was, an option on the table for you. So I pulled up the roster. I'm going to send it around. So if you are here, you could just initial by your name. I did send you all this information in a PDF format. So it's got live clickable links. You can hover over my name and it would take you to my contact page, as well as you can text my number. You can call it, whatever's most convenient for you. We do have locations at all 3 of our campuses. So I'm here in Tulare. My colleague Lisette Conway is at the downtown annex. So she oversees programs in HVAC, electrician training, and industrial automation. Jolene is in Hanford. So classes take you that way. She can assist you, but she oversees primarily the fire academy and the police. Daisy, she is located in Visalia at the Transfer and Career Center. We're now in Sequoia building, rather than above the bookstore, but she oversees administration of justice and nursing and allied health. Those seem to be, or child development, those seem to be her big programs. So like I said, I did send this to you. Frequently, we're hosting events throughout the semester, district-wide. One of the big ones we have coming up, and again, if I'm going to speak just on ag. Are there any ag division students in here? Oh yeah, oh yeah. So one of the big ones coming up. So in November, we're going to host kind of an open house for our entire ag division and have employers on campus. It's going to be a little more casual. And then in March of 24, so next year or next semester rather. We're going to have our all ag and trades job fair. Last spring, when we did it in March, we had right around 57 employers and about 200 students, and that was here at this campus. And that was the first time we did something like that. But a lot of the programming that we do as a department is really going to be targeted for specific majors. But like I said, I don't want to discourage any of you. My office is located here in this building, actually just 2 doors down from Mr. Jones. I'm in 109. Come see me. My door is usually open. Just pop in and we can schedule an appointment. Whether you had questions about career exploration, maybe trying to connect your major to some sort of career pathway, building a resume, or you've got an interview coming up and you're a little nervous about it. We can kind of go through some mock interview practice for you. So, any questions? It's kind of a lot of info. Like I said, I did send it. You're on the roster. I did send it to your giant email. So my contact information is there. Reach out to me. I really encourage you guys to take advantage of.
This is one of the good ones.
What's that?
Threads.
What? Oh, Giant Threads. Sorry, I just added it to the PowerPoint. So Giant Threads, I'm going to plug it right now. It's our mobile professional clothing trailer. We actually will host it here at the Tulare campus on Monday, October the 16th. And I apologize, I didn't include the PowerPoint in the email I sent to you, but I can resend it. It's got some dates for events happening at this campus. So that is, students have access to free professional clothing. They can access that twice a semester. Literally go online, they fill out a referral form. It's super brief. You can either schedule time to go for a fitting at the Visalia campus, or you can wait until we host it here on Monday, October the 16th in Tulare. It's brand new. It's nothing hand me down. So actually Career Services runs the trailer and the fashion department provides, the employees for it. So it's students within the department. You're going to go in there, they're actually going to fit you. So if it's slacks, I don't know what they can do with the shirt, but definitely slacks, you get a belt, pair of shoes. So definitely something totally fitted for you, whether you have a job interview coming up, need it for work, or just, some other type of, that would require a professional outfit in that type of setting.
It's free.
And it's free. You can utilize that once a semester. Any other questions, guys? Well, I thank you for your time.
Thanks, Cosmo.
Thanks, Mr. Jones.
No problem.
All right.
All right, limits at infinity. What's going on when we're no longer looking at the center of the graph? What's going on when X is like 1 billion or 10 billion? Or a gazillion? Well, no, that's not even far enough. Infinity is just farther than you can possibly imagine. What's going on when we reach the end of space? So limits at infinity are when we're looking at the graph along the x-axis, really far out. What's going on? So if we look at the graph of 1 over x, I'll put that up real quick. This is the graph of 1 over x. This is the x and y axis are right here, the black lines right here. And as it goes close to 0, we were talking about this on Thursday. But now what happens as we get way out here and we keep going further and further, the number further to the right that we get. The number keeps getting smaller and smaller and smaller and it approaches 0. So that's one of the important ones to know for limits as x goes to infinity. There are some situations like this one where we actually have a limit when x goes to infinity. Polynomials aren't one of them. We'll look at polynomials in a second. But like x squared, we know as x gets larger, y is just getting larger fast. X squared is getting larger faster. So some things don't have a limit, but some functions do. So if x can get as large as it wants and f of x is approaching some number L, we'll say the limit is x goes to infinity of f of x equals L. And then if we go the other way, x decreases. When they say decreases or increases without bound bound means nothing's stopping it. There's no boundary to how far we can go. So bound is like a very math term, a term they like to use in math. A bound. So we've got all the limit laws we looked at previously apply. Like we had the limit of f of x plus g of x. We could do them as two separate limits and add them up, and we could still add the final results. All the things we looked at before apply. And I want to make sure I give people time to write this down. So I know some people write it down. If you do like writing it down by hand, you can actually save yourself in time in class by looking it up ahead of time and like writing down at least one section on Canvas. The files are there. That way you can pre-fill it in and you're not like distracting yourself trying to write while, you know what I mean? I know how hard that can be as a student. Teacher keeps yabbering on and you're trying to write what's there. All right. Give it a little bit longer. See some pens still moving. Did anybody go by upstairs first? Was there a note on the door? Yeah. Hopefully, there's no one up there waiting. You went by, Matthew? I want to say I talked to you about that shit on Saturday.
You did? I was running late, so
Scrub.
I'm a force of habit.
That's what we're going with force of habit for 2 lecture classes up there. Is the habit already? I like it. It's your story. I'll let you tell it.
Fair.
So like we had one of the rules that we had was if we had the limit as x goes to infinity or some value a of f of x to the n, we could treat that as the limit as x goes to a of f of x all to the n power. That should apply here on this example right here. The limit as x goes to infinity of 1 over x cubed This is 1/x like that cubed. So if I have the limit as x goes to infinity of 1/x cubed, I can treat that as the limit as x goes to infinity of 1/x cubed like that. This interior part is up above. It's 0. What about the next one? The limit as x goes to infinity of x minus 1 all over x squared plus 1. What can I do here? Plugging in numbers now becomes no longer like realistic. So we got to do some algebra manipulation. The best thing you can do in a scenario like this, before I show you the quick and dirty rule in a second, is divide by the term with the highest exponent in the denominator. Highest exponent or highest degree. On the bottom. I know it's called denominator, but bottom is only 6 letters, the denominator is like fucking 12 or some shit like that. That's a long word. And it's 11. So, and this happens everywhere. So we have the biggest degree or highest exponent on the bottom is a square. So what I'm going to do is I'm going to divide everything by an x squared, or I'm effectively multiplying by 1/x squared on top and bottom. So if I do that, I have the limit as x goes to infinity of x over x squared minus 1/x squared. And on bottom, x squared over x squared plus 1/x squared. And as we clean that up, what do we have? I have 1/x minus 1/x squared on top. On bottom, I have 1 plus 1/x squared. As long as we multiply the top and bottom by the same value, all I've done is effectively multiplied by 1. We haven't changed anything here. But now we can apply what we were seeing right here. And with this right here, the limit is x goes to infinity of 1 over x. We can break this up into a bunch of pieces, pain in the ass. Or just apply the limit to each thing that's present. As x goes to infinity on 1 over x, we already had that, that's 0, this goes to 0. And just like the x cubed, or 1 over x cubed and 1 over x, this one goes to 0 also. And so does that. This ends up going towards, we have a limit as x goes to infinity of 0 over 1 after we've applied it. Like applied looking at it for infinity. So this is just 0. Everyone ready for more? I actually want to, if you're looking at the lecture notes, I'm adding something in between, so you might want to write on the back if you have those. Slipping a page. Looking at polynomials. We got our whole, we're doing the limit as x goes to, I'm going to write plus or minus infinity because either one does the same thing. And they're writing the equation twice kind of sucks. We've got C0 plus C1 x to the 1 plus C2 x squared plus C3 x cubed plus ... plus Cn x to the n. As long as there's at least one x in there, this is going to blow up to infinity. If n is greater than or equal to 1. As long as we got a variable present, it's going to blow up. My question for you is, which term here has the biggest impact? On the value or on y? Like let's say this equals y. Which term has the biggest impact on y as x goes to infinity? What do you guys think?
Maybe the one with the largest exponent,
Why do you say that?
because the larger the exponent, more it's like. Faster than really.
That's a pretty good reasoning. Let's take a look at like if we had like x was 10. That's not going to infinity, but I think we can see the idea really quickly there. Like if x equals 10, x to the first is just 10, x squared is 100, x to the fifth has 10 or 5 zeros, and I put the comma in the wrong fucking spot. So like x to the n, whichever number is the biggest, should have the biggest impact. It's going to infinity faster than anything else. That's right. the Cn x to the n term is dominating the behavior of this function. Let me zoom back out a little bit. This is a little too big. The Cn term is dominating the behavior of the function. So we could just as very well say the limit as x goes to plus or minus infinity of C0 plus C1 x1, oops, x to the first plus C2 x squared plus dot 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 plus Cn x to the n is approximately just the limit of the biggest term. Does that make sense? Just stop and think about it. If it's not what clicking, maybe you're looking at these as an example. What if we did x to the 100th power? Or like maybe we didn't start with x equals 10, but x was 1,000. So every time like 1,000 squared is already up to 1,000,000. And 1,000 cubed up to 1 billion. You can see that as x gets large, that the biggest exponent has the biggest impact. I wish someone had told me this while I was taking calculus, any of them at COS, just pointing it out, because it really becomes pretty helpful in higher mathematics. It also lets us do something for rational equations. If we have the limit as x goes to infinity or plus or minus of some polynomial p of x over some polynomial q of x, we can just look at the biggest terms on top and bottom. And when I mean biggest exponent on top and bottom. That last one we had the limit as x went to infinity of x minus 1 over x squared plus 1. The quick and dirty approach is, let's just look at the ones with the biggest terms on top and bottom. X goes to infinity. The biggest term on top is x. The biggest term on bottom is x squared. These will have approximately the same limits. Well, they will have the same limits because they're going to go to infinity. And that's just 1 over x when we simplify. And we know that's 0. On the next example, I'm going to do it both ways. I'll do it the long way, the way that the way it always works. That doesn't require this insight, this intuition. We can always divide by the largest or highest degree term on the bottom. We're still running. I want to make sure everyone's got time. If you guys took college algebra or pre-calc A here at COS, we actually did, one of the section is on what is the graph behavior. The N is the N graph behavior. What you're really doing, we haven't discussed limits in that class yet, but what you're doing to get them is you're looking at this very idea right here. So if you took college algebra, you did this before. We just didn't have limits on it. We didn't say limits. You look at what happened with the graphs. Anyone need this up longer? If you do, say something, otherwise it's going away in 3, 2, 1, bingo. All right, let me make that a little bit larger. That's a little small now. We're gonna do the limit as x goes to negative infinity. The numerator will be 4x squared minus 3x plus 8. The denominator is 2x plus 3. The highest degree term on the bottom is 2x. So 2x is the biggest term. We're just going to divide by the x. I will multiply the top and bottom by 1 over x, which is the same as dividing by x. So each thing on the top and the bottom, just divide by x. If it helps, write it out like I'm doing right now. At some point, when what we're doing really clicks, you're going to see this as a waste of your time writing this step. But I want to make sure everyone knows what the hell Jones is talking about. This just equals 1. Remember, we can't change anything. That just equals 1. Because I'm dividing a number by itself. 1 over x divided by 1 over x. And now let's clean that up. That should be a negative infinity. This is on top 4x minus 3 plus 8 over x all over 2 plus 3 over x. All right, so we saw that the 1 over x's, which is the same thing, is going to be 8 over x or 3 over x. These terms go to 0. So we're just looking at what happens with negative infinity as we apply it to there. We've got 4 times negative infinity. That's not really a thing we can do, but it kind of shows what's going on. This is going towards negative infinity. So the limit's going to be negative infinity, which means there is no limit. All right, let's take a look at the quick and dirty approach. I know exactly who I learned that phrase from. It was the teacher at UC Merced that taught me this rule in itself. I think that's why I said it. He had a question on like an exam with what happens as x goes to infinity of this polynomial, and like no one in the class fucking really knew. We didn't like realize what he was going for was it follows the biggest term. It really matters. But if we do that here, just look at the biggest term on top and bottom. On top, it's 4x squared, and the bottom, it's 2x. This is really saying what happens. This will do the same thing as the limit as x goes to negative infinity of 2x. Which is clearly negative infinity or doesn't exist. What's his name? We always called him Dr. O, but it was not like Dr. Owens, the engineering teacher. He was great. He had side fucking chops. He looked like fucking Wolverine. I had a teacher that looked like fucking Wolverine. It was great. Let's see a chat question. Not that they're negative, Carla. It's that it's negative infinity. Negative limits are just fine. So Carla asked, when the limits are negative, is it always DNE? No, it's not always DNE. It's the fact that it's going to infinity. Good question. So something handy to, well, I'll do that at the end. No, yeah, we'll do it at the end. Let's talk about what happens with radicals. Now we got limits involving radicals. So the way you address this radical situation is we're gonna have two scenarios. If x goes to infinity, let me draw a line separating these two ideas, these two problems. If x goes to infinity, divide by the absolute value of x. You might have to do it more than once, so maybe x to the n, which equals the square root of x squared to the n, kind of thing. Sometimes a lot of times you'll just get away with n equals 1, but in this problem we don't. If x is going to negative infinity, you do something similar. We're still dividing by the absolute value of x. And if we need it at a higher power, we'll do it at a higher power. So that's the square root of x squared, or it's negative x as x goes to negative infinity. So how do we go about doing this? Let the radical in the problem guide you. We have the square root of 9x to the 6th right here. We have the 6th power. We want to divide by something that will have the square root of x to the 6th. So if I did for this problem, if we used absolute value of x cubed, we would have, I don't know that I like that. Yeah, it's technically what. Yeah, that's what we're doing. We're going to have this as x to the 6th power. Rather than x squared. And then the other half is negative infinity. Or we have negative x cubed. Which is what we'll use for the bottom. So this is just negative x cubed. We don't need the parentheses anymore. Whoa. God damn it, keep hitting it. So I have the limit as x goes to negative infinity. The top gets divided by that x to the sixth power. Well, square root of x to the sixth power. And the bottom gets divided by negative x cubed. Now, this may be been a while for some of you. When you're dividing by radicals, a fraction or a radical divided by a radical, you can put them all under one radical. So this top part, I should have a negative there. This is the same as limit as x goes to negative infinity. The top is 9x to the sixth over x to the sixth minus x over x to the sixth. Bottom, if we separate it out, it is x cubed over negative x cubed plus 1 over negative x cubed. I'm writing more steps than I would if I were doing this on a test, but I want to make sure everyone follows along with what's going on. So, what happens if we keep going? The top is just 9 minus 1 over x to the fifth. And the bottom is negative 1 minus 1 over x cubed. Yeah,
Sorry to backtrack, but the rules say if x approaches negative infinity, you divide by x squared. Right?
yes, or some power of it.
Oh,
So like, if I divide by x squared, it's not gonna do enough to get rid of the radical here.
okay.
What we're trying to do is take or like address the biggest exponent in the radical. Maybe I'll add that down here. I should have wrote that. Do enough square roots of x squared to address the highest exponent in the radical. Yeah,
And why is it negative x cubed instead of just? Like, why are we dividing by negative?
because using the square root out here isn't really all that helpful. And what we're really doing is dividing by absolute value of x. One definition of absolute value of x is the square root of x squared. But if like x, let me just point it out real quick. If x is like negative 1,000, the absolute value of x is 1,000, right? Everyone's good with that. But this is negative x. Because x is negative 1,000. If I take the negative of that, it makes it positive. So doing the absolute value of x when x is negative gives you a negative x. It is it's a one of those mind fucks. You really gotta stop and think about it. I think if you look at it right here, you'll see it. Like if I make negative x right here, negative x is 1,000. But that's the same thing as the absolute value of x. So if you start off with a negative x, doing the negative one gives you absolute value. It is one of the ways absolute value of x is defined. Absolute value of x is a piecewise function. So, any other questions before we continue on it? Everyone good? Yeah. I assume down means this direction? Okay. Now, as we apply our negative infinity, any term that has the x's in the denominator goes to 0. This is going to go to 0. That's going to go to 0. And we're left with square root of 9 over negative 1, which is negative 3. It's a tricky one. Anyone? Oh, people still writing. Just hold your horses, Jones. Does anyone need it up longer? Raise your hand if you do, otherwise we're gonna go on to the next page and all right, let's do it. Now, the first thing you should always try to do is just try to separate these out. If I write this as the limit as x goes to negative infinity of square root of x squared plus 3, and then I do plus the limit as x goes to negative infinity of x. What does the first one equal? I'm too close. If I plug in, like I can, it doesn't cause a domain violation, does it? I can plug in negative infinity. What's happening to this one right here? This isn't a trick question. I'm not pulling some shady shit.
Goes to infinity.
It goes to positive infinity. Yes. Because it gets squared, so the negative goes away, but now we've got the square root of infinity squared. You just get infinity. What about the second one? The limit is x goes to negative infinity of x. negative infinity. That's right, that's correct. So I have negative or infinity minus infinity. This is one of the indeterminate forms. Wow. Let me write it bigger where my letters don't look like I don't know how to spell. Indeterminate form. Those are 0 over 0, infinity over infinity, and infinity minus infinity. Those are our indeterminate forms. These are usually the ones where we can do some manipulation. Yes. Thank you. We can do some manipulation to clean it up. We did this in 1.2. If you, and I don't know that I pointed out in the lecture or even in that little 10-minute video I made, but every time I did the problem, I plugged it in to see what it looked like, and we had 0 over 0 every time. And so we ended up manipulating it either by dividing by X or multiplying by an X. We did a bunch of shit in 1.2 to manipulate it. We can manipulate this one here as well. And it's not really all that intuitive, but you did something very similar in 1.2. What did we do when we had a radical? How to do another term? And it was in the denominator. We multiplied by the conjugate. So let's do that here. Let's multiply by the conjugate on top and bottom. What the hell's going on? Multiply by conjugate on top and bottom. So I have the limit as x goes to negative infinity. I have the square root of x squared plus 3 plus x. That's what we start with, all over 1. And I'm going to multiply that by the square root of x squared plus 3 minus x. And I'm going to do this on top and bottom. On the top, we have a plus b in the first parentheses, a minus b in the second parentheses. That top is going to clean up to a squared minus b squared. So a is the square root of x squared plus 3. So a squared is that, and then we have minus b squared. B was x. On bottom, we don't have anything special. This difference of squares formula shit gets used a lot from algebra. Eventually, it becomes second nature if it's not already. What happens if I square it though? What's the top look like after dealing with all those squares? Bottom isn't changing, we're just gonna write that. If we square the square root, what happens? The square root's gone. This first part is just x squared plus 3 And then we have minus x squared. So if we clean that up a little bit, we just have a 3 on top. Now, this might look like trouble still, but it's actually not. As we plug in negative infinity, this is the square root of negative infinity. We just did this part up here. This part was positive infinity. But now we're doing minus negative infinity. So we really got infinity plus infinity, or 2 times infinity, which is still just infinity on bottom, which means this is going to 0. How is that for some crazy shit? And I'm guessing who here is sitting here thinking, how the fuck did he do that? Right. I've taken classes on this. I've learned I didn't figure this shit out. Someone else, someone much smarter than me, probably fucking Newton or someone like that, you know, someone that like is in textbooks, they figured all this shit out. They wrote it all out. And we just pass on their knowledge. Someone got creative and said, you know what? Let's try the conjugate and take a look at it. So you're going to have to kind of do what I did. Just like learn off someone else's insight. Newton or whoever figured this shit out, way to go, Newton, or Galileo, or whoever the fuck it was. If you see a radical added or subtracted something else, throw a conjugate at it, see what happens. If it doesn't work, you just have to erase a little bit. Okay? Calculus, and you're going to have a lot of trial and error shit as you go through this class. Because there's going to be some problems along the way. There's like, I'm not sure what I can do. So you just got to try the things you know until one of them works. Okay? You will take the wrong path multiple times in this class. I promise you. But if you stick with it, you'll get there and you figure it out. We're going to take a break, but I'm going to share one little more piece of information with you before you go. This is worth writing down. I'm not going to prove it, but since we're doing infinity limits, I'm going to put it here. The limit as x goes to infinity of 1 plus 1 over x, all raised to the x power. This is some bullshit right here. Watch this. This equals e. Like good old e to the first power. That e. E is in the exponential. 1 plus 1 over x to the x power as x goes to infinity. That's fucking crazy. Just is. Like I said, someone smarter than me figured that shit out. I don't know that you need to memorize it. It should pop up again, but we'll address it later. If you want to take a 5-minute break, please do. I'll pause the recording real quick. Or is there any questions? So we're going to skip 1.4. We're going to cover it like the end of the semester. It's like the proof section for how you get a lot of this stuff. If you look up the examples and like the web appendices on how you prove some of the stuff. It uses something called the delta epsilon proof. It's a pain in the ass and it's not important to the big picture unless you're going to go into pure mathematics and you want to start proving all the rules of the universe. Other than that, most people are willing to accept the rules as they are without needing to have them proved. Like you don't understand why your cell phone works, you just use it. So section 1.5, we're going to talk about continuity. Continuity looks similar to the word continuous because they are related. So we're going to say a function f is continuous at a point if the limit as x approaches c of f of x actually equals f evaluated at c. This applies three things. It's defined there. F of c has to be defined, otherwise we couldn't say it equals it. So this is kind of saying no holes or asymptotes. Well, really, no holes. No, it's an asymptote as well. The limit as x approaches c as f of x exists. So this is saying that it equals the same from the left and right. X approaches c positive f of x is the same thing as the limit as x approaches c from the left. So they're kind of like converging at a location. And 3 is saying the limit as x approaches c of f of x equals f of c. This one is saying these two actually just happen to equal what happens if we plug in c. We should be able to plug in c. So basically, there's no breaks or holes at the point. No asymptotes, no holes. Even something like this where we have a hole, but there's a point below, it's not continuous because an easy way to test it is, do I have to lift the pin? If I'm going along the line, do I have to lift the pin to draw the graph? So looking at this graph here, where do we have, what values of x have? Where is it where it's not continuous? These are called discontinuities. So like where this is violated, breaks and holes are what we call the discontinuities. Asymptotes. So what values of x on the graph have these? Anyone want to answer? But everyone's still drawing the writing and drawing. I mean, hold your shit, Jones. Slow down. What's the rush? I realized I was a dumb shit. I set up next week to do 1.7 and 1.8 on Tuesday, and like a fucking champion said, let's do the test on fucking Thursday. That's fucked up. We're changing that shit. I'll adjust the syllabus, but I'm just gonna, and I'll send out an announcement. Next Thursday, we're gonna do 2.1 and 2.2. And that way you can go over like I'll have a review sheet for you. You can go over the review over the weekend and we'll do the test on Tuesday. That way, it's not like you have 2 sections and then 2 days later a test. That sucks. I don't need to do that. We'll just start delving into 2.1 and 2.2 before that. Does that sound better than a fucking test next Thursday? Does anyone want the test next Thursday? No one? Good, because I don't want it next Thursday either. That's a way to discourage a lot of people and everybody just runs away. Now, we still have to have it, so it'll be the following Tuesday, but. All right, so what values of X here have discontinuities? Where are the breaks and the holes on the graph? X equals 1 has a discontinuity. Right there. It's 3, that's 5. Where else do we have discontinuities? Go ahead, Matt. Or Matthew. I forget. Is Matt okay or Matthew?
Whatever's fine.
Whatever you'd like to be called is better.
Matthew's okay.
Okay, that's it. X equals 2, yeah. There's a hole and there's a dot above it. Is there any others? Yeah. X equals 3. Do you have any others? 5. Do we have any others?
2, why not?
Yeah, two's 1. You're right. There's no other ones listed. Okay, so X equals 1 doesn't have a special name. This is just called the discontinuity. It says classify the discontinuities. That's what we're doing right now. We're going to classify them. They have different names. They're all discontinuities, but some of them have like names just so you know what's really going on there. At number 2, or X equals 2, the graph's here and all of a sudden it jumps down, drops down to this one. If it was going the other way, it might jump up. This one at X equals 2, where the line starts or stops and then restarts somewhere else, is called a jump discontinuity. Yeah,
Would X equal 1, it wouldn't be a hole. Since it's like an open circle.
it's a hole, there's a hole there.
But we don't actually call it a hole.
No, they just call it a discontinuity. If you're gonna apply, it is a hole, yeah. But they just call it, they like to use the fucking as big as words as possible. Right? Denominator and numerator, really? Cause like top and bottom are really short, where top is really short. A hell of a lot shorter than numerator, and that's what they came out with, numerator. So X equals 2, the graph jumps. Pin has to lift the page to go to the next spot. X equals 3, we have an asymptote. It's going to infinity there. The limit's going to infinity. This is an infinite discontinuity. And X equals 5 is a special case. Number 1, f of c is defined. At X equals 5, f of c is defined. It's 2, it's right there. The limit as X approaches c of f of X exists. It's approaching 3. The only rule that's broken on at X equals 5 is that the limit doesn't actually equal the value. This is where you have a hole in the graph, but you have a point somewhere above or below it. Now, if we could just move the point up, or if it was above it, move it down and plug it in, we wouldn't have a discontinuity. We're not going to actually move it. The idea is if we could move the point and do it, This is called a removable discontinuity. So those are the names. That's your Trivial Pursuit questions, your fucking I Watch Jeopardy with Grandma question. You think that's a test question? It's a fucking waste of time. It's only handy if you're reading something and you know what they mean and someone uses the phrase. Because in all reality, you're not gonna walk around and talk about infinite discontinuities. Right? This is more of when someone else is trying to fucking show off with their big vocabulary. Everyone's got someone like that in their life. Someone that knows a lot of words and they like to use them just to try to make everyone around them feel stupid. That's what this language is for. So that's how continuity works. Basically, it's continuous if the line crosses it there. So then we stop looking at what happens at individual points. And we start looking at what happens on a region or an interval. So we'll look at the open interval from A to B. And open means we don't include A and B. All the way up to A and all the way up to, or all the way down to A and all the way up to B are in the region, but we don't actually have A and B in the region. F is continuous on that interval A to B if F is continuous at every point within the interval. Now, if we want to include the endpoints A and B, we call it a closed interval, and we have a couple more criteria. The first criteria is that it's of course got to be continuous within it, but then we have to look at what's happening at the endpoints. So 2 and 3 are the only new things for a closed. And we are looking at something like, let me get a different color pen. We are doing some graph. And like if this is A and this is B, we're looking at like what's going on there. So like having a picture like helps make the rest of it kind of make a little bit more sense. So for it to be continuous on the closed interval, it says F is continuous from the right at A. That is, the limit as x approaches A from the positive side of f of x equals f of A. It means the point is that at A, x equals A is actually on the line still. You don't have a discontinuity exactly at the endpoint. Okay? And then if we do it for B, we're going at it from the left. As x approaches B from the left, it also has to equal it. A handy way of looking at it is coming up to right here. And let's say this right here is A at x equals 0. And this right here is B. So x equals 0 is my A. And x equals 1 is my B. And if we look at that graph here, if I write this down here, I have it going like that. Like if I copied it down. This one works, this one doesn't. So this would not be good for the closed. I can't have one on the list because the value is undefined at one. Function is undefined at one. If you think about what it means, the continuous line means it's an unbroken line. It means everything, like you should be able to draw the whole fucking graph in that region without lifting your pen. Right? Folks are still writing, give them a second, then we'll turn to the page, look at some examples. You guys ready? Nope. I see spin going, sorry. Not trying to rush, my bad. Take as long as you need. We're not scheduled to finish 1.5 today. So if I do, I'm probably going too fucking fast. There's no way in hell I'm gonna finish 1.5. That's 4 more fucking pages. That's crazy talk. All right. Anyone else need up longer? Onward. Let's take a look at the following functions and go, where are they continuous at? What regions do we have continuity at? In fact, I want you guys to stop and work on this for, 5 or 10 minutes, work with each other, talk to your peers, like work through these problems and figure out where you think there might be discontinuities. And if you do, what kind of discontinuity are there? Yeah,
Should we graph it?
if you want to, please do. It might help you. Oh, I'll pause the recording of the video. No point sitting here recording you guys working quietly amongst yourselves or with each other.